Hello, I'm Yuguan from Alibaba Cloud. In this talk, I'll introduce Crux, a communication scheduler of GPU clusters for multiple deep learning training jobs. In deep learning training, to better utilize GPUs, most GPU cluster providers try to serve multiple deep learning training jobs with one cluster. We call it multi-tenant GPU clusters. The goal of such a design is to optimize GPU utilization, that is, to keep more GPUs working at all times. Based on our production experience, GPU utilization is the most important optimization goal because high GPU utilization means the cluster can do more computation in a given time duration, making more profits. However, multi-tenant GPU clusters introduce a problem, communication contention between jobs, which significantly degrades GPU utilization. Let me show you one example. Suppose we have a GPT model running in the GPU cluster. If we run another BERT model concurrently, the traffic of two jobs need to pass the same switch link and compete for the bandwidth. We call this communication contention on network path. For this case, our experiment shows that the iteration time for the GPT model is increased by 11%, and the GPU utilization is dropped by 9%. Contention can also happen inside a host. When two jobs occupy GPUs in the same host, they may share the PCIe link or NV link, and thus contention happens. So, is communication contention frequent in production? The answer is yes. In our production-based investigation with more than 2,000 GPUs, there are 39% of jobs ever experienced communication contention with others, including contention on network switch, network links, and PCIe. So we say communication contention between jobs should be handled carefully. So why existing work does not help? First, most multi-tenant GPU clusters have job schedulers. The job scheduler locates each job to different hosts and tries to reduce resource contention, including communication contention. However, with the number of jobs increases, communication contention can be reduced but cannot be completely avoided. So, even the jobs are carefully located, we still need a communication scheduler to make path selection or assign higher priorities to data flows of important jobs. It helps to further mitigate communication contention. Unfortunately, existing communication schedulers focus on pure data transmission jobs. They try to minimize completion time of each flow or try to complete the flow transmission before the deadline. So they are unaware of the flow pattern of deep learning training jobs, like iterative traffic burst. They are also unaware of the goal of GPU utilization. So we need a communication scheduler of deep learning training jobs for multi-tenant GPU cluster. To schedule the communication between jobs, first we should know what kind of jobs is more important. Let's see an example. Suppose we have two jobs in the cluster. Job 1 occupies 8 GPU hosts, and job 2 occupies only 2. That is, job 1 is 4 times larger than job 2. Intuitively, when job 1 experiences contention, more GPUs will be impacted. From this example, we know that larger jobs may get higher priority. But what's the reason behind this? To answer this question, let's dive deeper into the deep learning jobs. In deep learning training, the process of computation and communication always depend on each other in one iteration. It means that a job always needs to transfer a certain amount of data to unblock a certain amount of GPU computation workload. When job 1 and 2 compete for the network, if the network transmits data of job 1 first, it can unblock much more GPU workload than job 2. So prioritizing it can make much more GPUs keep working. As a result, job 1 is more important than job 2. So our first insight is larger jobs should be prioritized. Then we find that even two jobs occupy the same number of GPUs, their importance may still be different. Based on our experiment, for example, a job of longer computation duration is more important. And also, a job of shorter communication duration is more important. Then we find that the common point of the above insights, GPU computation intensive jobs are usually more important. To quantify the importance of each job mathematically, we propose a new concept, GPU intensity. Generally, intensity can be represented by dividing the amount of computation, W, by the amount of communication, T. It describes how much computation is blocked by a certain amount of communication. And we prove that optimizing GPU utilization is equivalent to maximizing GPU intensity in communication scheduling. Details can be found in our paper. Based on GPU intensity, our key idea is to prioritize jobs with higher GPU intensity. In production GPU clusters, communication scheduling are usually achieved by path selection and priority assignment. Next, I'll introduce challenges and our solutions to prioritize GPU-intensive jobs by path selection and priority assignment. Let's dive into the first challenge, make path selection to avoid communication contention. Most GPU clusters provide multi-layer network switches, so there are multiple paths between GPUs. Although traditional hash routing can balance the load of each path, when the number of jobs increases, contention is inevitable regardless of the path selection, and the GPU utilization is degraded. So the challenge is how to design a better routing strategy to reduce GPU utilization loss in communication contention. Back to our key insight, GPU intensity. In fact, as the number of jobs increases, we cannot completely avoid communication contention. But it is possible to avoid communication contention between high GPU intensity jobs. And we already show that jobs with higher GPU intensity is more important in GPU utilization. Here's our solution. Suppose there are 4 deep learning training jobs running in a GPU cluster. We first sort the jobs by their GPU intensity. Then we choose the most uncongested path for each job one by one, from the highest GPU intensity one to the lowest. Now, we select an idle path for job 2, and then select a different path for job 1 and job 3. As for job 4, there is no more idle links, but we can still select the most uncongested path for it. This strategy does not avoid all communication contention between jobs, but it encourages GPU-intensive jobs to select different paths from each other. In this example, 2 high GPU intensity jobs, job 1 and 2, are assigned different paths. So this path selection reduce most GPU utilization loss caused by communication contentions. The second challenge is how to assign priority with limited priority levels. In real-world GPU clusters, data flow priority control is implemented by differentiated service code. Usually, it provides no more than 8 priority levels. Some of them may already be reserved for special usage, such as control message and network diagnosis. So we only have few available priority levels for flow scheduling. However, in one cluster, the number of concurrent deep learning jobs is much greater than the number of available priority levels. So it is not possible to assign a unique priority to each job based on its GPU intensity. Most jobs have to be assigned equal priority levels, leading to random communication contention. So how to compress the priority assignment but try to differentiate jobs of different GPU intensities? We find that although there can be many concurrent jobs, usually a job only has communication contentions with some of them, not all other jobs, just like this matrix. Only red colors means communication contentions. Based on this insight, we can build a direct acyclic graph to describe potential communication contention between jobs. Each edge from A to B represents job A and B share the network path, and A has higher GPU intensity. Suppose we want to assign 3 priority levels to this job. The problem is transferred to finding the maximized 3 cut for the graph. That is, we split the graph into 3 subsets, corresponding to 3 priority levels. We want to cut down as many edges as possible, because for jobs with communication contention, it is more necessary to assign different priorities to them. We design an efficient dynamic programming algorithm to get an approximate solution. Details can be found in our paper. We have built Crux in our production for daily communication scheduling. Our implementation needs to address the following issues. The first problem is how to get job information, including computation workload W and communication workload T, to calculate GPU intensity I. To ensure a new job is measured accurately, we always first assign the highest priority to it to make sure it will not be affected by other jobs. Then we can measure its computation and communication workload. The second problem is how to get path information in the network. Normally, network switches rely on hash to forward packets based on port numbers. Therefore, we can explore all possible paths by changing the source port of packets. The third problem is how to execute the path selection and scheduling decisions. We specify the UDP source port of each packet to select different paths, and specify the type of service, TOS, in IP header to assign priority. Our evaluation consists of 2 parts. Our real testbed evaluation runs models on GPUs to evaluate the effect of Crux scheduling. The trace-driven simulation uses our collected dataset to evaluate Crux in a larger scale cluster. Our testbed evaluations run 3 models: ResNet, BERT, and GPT. The left figure shows the job completion time, JCT, of each job, with and without Crux. We can see that Crux prioritizes GPU-intensive jobs like GPT and BERT, with a small performance reduction in ResNet. As shown in the right figure, such scheduling brings up to 13.9 GPU utilization. Here are the results from our simulation evaluations. Crux outperforms state-of-the-art solutions and offering much better GPU utilizations. The dataset used in our paper is now open sourced. We collect information of our multi-tenant GPU clusters for 2 weeks in August 2023. The cluster consists of 800 hosts connected by a 3-layer CLOS network. The data consists of topology information and job information. As far as we know, this is the first public multi-tenant GPU cluster dataset for large deep learning models. Feel free to click on our link and download our data. To summarize, we find that communication contention between deep learning training jobs needs to be handled carefully. And we propose Crux, a multi-job communication scheduler, to optimize GPU utilization by path selection and priority assignment. Finally, we evaluate it by both test bed and simulation. Thank you. Questions are welcomed.